really good performance. Because it's someone else's computer, we need to make sure we're able to put new objects in my object store and pull them when we need to. So they have really good performance, and they achieve more than 3.5K quick requests per second. Specifically, this was tested on S3, 5.5K get requests per second per prefix. And you can think about it as my URL, right? I have prefixes and I'm moving in between things. It auto-scales automatically. I have unlimited storage space. Essentially, the more I can use as much as I want, as long as I'm able to pay. And it has around what we call the high 9 percentiles, 11 9 percentiles of availability, which is really, really high because it's managed by the big companies, and they take care of that. In terms of cost, there are different layers of cost. There are different tiers of cost, where the cheapest one can be 0.023 per gigabyte, essentially, versus more expensive for storage that is faster, more reliable. Same thing goes with network, because essentially we're moving the data along the network. If we think about our infrastructure, we have our storage, we have the network because it is a distributed system, and then we have our different GPU or CPU that does the compute. So we have the actual machines for the compute. We get a question. When you say 5.5 get requests per second, how much data can you get? That's a really good question, because the data is limited on this request, and it really depends on network and efficiency. We'll touch upon it, and there's also optimization for a specific object. So you can optimize to get the most out of your object stores by saving it in a specific size. So if you're familiar with the world of HDFS, we called it blocks back then, and if the information that you want to store on that specific block didn't fully utilize all the block, then you'll have not idle, but basically it will save it as a block on disk, and the little piece that you have left, you cannot utilize it because you either save it in a block or not. And are the datestamp hierarchy in terms of folders for the files? Would there be a folder for years and subfolders for months? Yes, and this is data modeling. And that depends on what we're looking for. So 100%. We can have subfolders, and we can save it according to a specific date, so it's easy for us to find the date that we want. Another thing that's really good about object stores is user experience. It has relatively mature client for both Azure, S3. GCP is slowly growing as well, Min.io. They have strong consistency up until 2020, at least for AWS. It used to know that they didn't have strong consistency, but now they have strong consistency, which is really, really impressive. There is a way to look into the data that's available there. For AWS users, it's AWS Storage Lens. For Azure users, you have the Storage Explorer that you can look at. It's really good. And it's feature rich, which means if there's events, we can work around events. If I'm adding more things into my object store, I can trigger some action, permission, replication if I wish to, and many more. And last thing, it's very highly connected, so it's easy to work with them. We can use them with a lot of open source tools and a lot of other tools that we usually have in our infrastructure, like Snowflake, Presto, Apache Spark, Kafka, and all of those good stuff. If anyone here works with these technologies like Kafka, Spark, or Presto, Snowflake, comment in the chat. You can say yes, or you can say the name of the technology. If you work with all of them, kudos to you, well done. It's a good list of technologies to know and to work with. All right, Kafka, awesome. Databricks, awesome. Really great technology, all of them. Kudos to you, my friend. It's a lot of things to know and learn. This is great. All of these technologies are really in high demand in the industry. Redshift, Kafka, Iceberg. Yeah, nice, good combination. All right, so we talked about all the pros and what we can do with ObjectStore. Let's talk about what not so great with them, especially in the cloud. Oh, and I see more Kafka, Presto, Spark, mostly Spark. Awesome. So specifically in the cloud, there are some things that are not always 100% great. I know you're excited for this part. Billing is confusing. Understanding what we pay for, why is it growing now, etc., can be really, really confusing, and that really depends oftentimes on where you send your data and which regions you do your compute, because there's a networking effect going there. Specifically with AWS, it's ingress that is free, outgress that it's that costs that we're paying for. So this is a big one. Often there's atomicity and consistency are a little bit confusing. For example, what happened if I do a rename to my directory, right? We just talked about the strong consistency that we now have, but when I do rename, something works slightly different there. So it's still, there's nuances that I need to understand. Or if I need to move some, or I need to do some operations around that. There is lack of concurrency control. So if I want to do multiple puts or multiple gets, it's a little bit hard to understand how it's being controlled and what is the order of things. Atomicity doesn't work on more than single object. And you can imagine, like, you can ask yourself, why is it a problem? It's only my CSV file. I need atomicity on my CSV file, and that's it. But oftentimes, it can be that we have a table that's more than one CSV file that we want to work with in an atomic manner. So because we don't have that atomicity over more than one single object, then we start having problems. So it's great that we have strong consistency, but if my table is spread across multiple objects in my storage, then it means nothing because I won't have the atomicity for the table as a whole, and this is where problem starts to occur, especially if you want this infrastructure to serve its customers internally. Metadata scalability, like listing itself is slow. So I want to look at all my objects in my object stores, and I want to list it. It's on Amazon S3 is very, very slow, and it often returns up to 1,000 results at a time. And this query, I cannot run it in parallel at all. So that makes it very, very hard. Sometimes the API can be a little bit outdated. I don't know how many people here work with API that returns in XML. You can write in the chat if you ever worked with an API that returns an XML. It's very hard to parse programmatically oftentimes. So the API is a bit outdated in these terms, and there's no like standard signature mechanism to work with it. Security is very hard to manage on S3. You have to understand how their policies work, and their policies are very generic, so you can basically achieve anything you want. You need to understand how the IAM policies attach to users and groups, etc. When we think about a data lake and we think about how it serves our customers at the end of the day, we always need to think about the metadata support for it. It's not only the list of files is available there, but what does these files represent? What do I have there? Which tables? What is the type sometimes that I have? I don't have any specific way to fetch that information with a single call to my object stores at this point. It has sometimes unpredictable TTFB, time to first byte. That means if I'm doing get, I don't know exactly what's the time to first byte, but it actually starts to run, and their machines, the cloud machines, become warm and interact with me. So let's say and a lot of folks here are using Spark. So let's say my Spark job is up and running. It needs to read some information, or it's or anything that comes up, it might mean that it will take a little bit longer than I expect just because it will get stuck on calling to object stores to get back the information. There's only overrides, so there is no support for append or modify, which makes it really, really hard oftentimes. If I have corrupted data in my production system, in my S3, then it's hard to fix it because of all the things I mentioned before. It's very slow to list all the files that I have there. It's very slow to copy the data. If I have a lot of data and I want to copy it, for example, with S3, I have buckets. It's the notion of buckets. So if I have a bucket, I want to copy it to a new bucket, then this operation can be very, very, very slow. Some people copying gigabyte of data or terabyte of data can expect like sometimes hours of the copying. Depends on how much data you have. They're also not so great if I need to test new modified pipelines or if I need to guarantee quality of the data. This is not something that my storage does out of the box. This is something that I need to be able to support on my own. So how do we solve all of these challenges, right? We're here to talk about all of the cons and pros and also solve some of the challenges and know the strategy for them. So what we're going to do is going to embrace file system directories. Like beautifully mentioned in the chat, we want to save the data. We want to save the data in a way that it's easy to extract. It's easy to find, it's easy to index, and also leverage some best practices that exist in databases. So if anyone worked with things like Oracle or things like that, you might have seen a lot of great best practices. Sometimes these are abstracted, so we don't interact with them. But if you dive deeper into what they provide, it's actually very, very interesting. I see some comment about combining Athena and S3. Yeah, that's amazing. All right, so we handled our basic, and now our goal is to level up. So we want to make the first improvement. So our first improvement is actually moving from CSV to Parquet. Anyone here knows why we want to move to Parquet and want to share in the chat? Did you ever work with Parquet? There's a lot of Spark users, so probably you have. And most of the time, the goal for us to work with Parquet is because it's columnar. Columnar means I can query the data is being saved on storage in a column basis. So it doesn't save it row by row. It's actually my whole file is saved in the order of columns. So if I want to filter in a specific column, reading is going to be much, much faster. And yes, like someone beautifully said, compression. It is compressible. And there are multiple formats or there are multiple algorithms for us to leverage for compression. Spark has out-of-the-box compression that it uses. It works wonders with Parquet. And it's also a little bit complex because we can't really see the files, right? So if we want to open a Parquet file, we have to use some analytics tool in order to see it, or some other tools in order to understand what's available there because of the compression, because of the columnar. So this is my half step up. And it's going to operate only at the object level because I'm putting my Parquet file directly on it. So taking another half step is the modern table formats. Someone said discovering Parquet was a lifesaver, especially partitioning. Yeah, 100%. Sharding, partitioning, and working with distributed data on disk is always very interesting. Thank you for sharing. We're leveling up. So we're talking about modern table format, which is a really, really, really interesting topic. So we have Parquet, and now we know that when we look at Parquet, we actually look on a specific table that it's saved. It's partitioned, is split on disk in a way that it's easy for us to access it because we now call it a table. And a table is a table's level often comprised of optimized data files plus some transaction log that comes with it. Mainly used Hadoop storage format. I think it's quite similar. Yeah. Parquet is highly used in Hadoop as well. Hadoop world. Okay, so we're leveling up to tables, and now we're speaking in the level of tables. If I have my CSV, essentially it's a tabular format that I work with, right? It has a structure, at least very close to a structure, and something I can work and look at what are my different columns. Similar with Parquet, it's a columnar. We have columns, we have types that we work with. So essentially, at the end of the day, is a table. And now we're going to level up to table formats, and we're going to go over a couple of table formats. And so Databricks has an option to use either Parquet or Hadoop. Okay, interesting. I didn't know that. That's very cool. I wonder maybe it's part of the migration features that the wonderful folks at Databricks are offering. All right, and transaction log. So what are table format? At the end of the day, they help us organize a data sets file to present them as a single table. One single table, organized, easy to use, easy to query. And it helps us answer the question. It's really, really critical, especially for all the DevOps and data engineers here in the audience, is what data is in this table? What's available? What can I do, right? So we want to be able to operate on table level, and this is what table format brings us. You want to be able to define schema. We want this schema to be available for everyone who interacts with this table. We want to be able to traverse different versions. So we want to have version control or some label of versioning or time travel to my tables. And I want to be able to upsert automatically, something that wasn't available for us in the Hadoop world for a lot of good folks here that used to work with Hadoop. Hadoop, we can't upsert, essentially. We have to delete, rewrite. There's a whole process around that, but we want to have atomic upsert operation to add things to my table. So in the industry, we have 3 highly known, highly respected, highly loved implementations. One is Iceberg, the second one is Hoodie, the third one is Delta Lake. So we're going to take another step in and dive into each one of them so you all can understand them. And this is usually the step where people have a lot of questions. So don't be shy. Feel free to ask and share your thoughts. The first one is going to be Apache Iceberg. So Apache Iceberg is a project that came out of Netflix. It was developed internally for Netflix. It was developed specifically for fast reading. So if I have a lot of data, my data is stored. It's not a live data that constantly change and evolve. It's stored static data that sits there, and I need to be able to relatively query it fast. And I need to have multiple operations query the same data or different permutations of that data. This is what Iceberg was initially designed for. It has very similar capabilities to what we know with SQL tables and traditional databases, yet it's fully open source. So it's really nice that you can go in and see how it works, and it works beautiful with Spark, and Presto and a lot of our technologies that we mentioned here. And the access go through a metadata file. So like we mentioned before, we have the tables itself, and we have some log that help us manage and understand what exists. So here we have 3 different layers of metadata that Iceberg implements. So what it does, it tracks point-in-time snapshots, so a specific version, point-in-time snapshots, by maintaining all the deltas as one table. So that's really interesting. So each snapshot provides me with a complete description of the table's schema, partition, and file information. So it looks at it as a whole table. And it helps organize this snapshot metadata and hierarchical structure. So I can employ fast and efficient changes without redefining all the data sets from scratch. So it helps me things like with schema evolution if I need to drop, if I need some minor update or minor renaming or anything related to that. Not big ones. Big ones are expensive. Minor things, if I need to optimize read, and so I need to do some repartition of the data or something like that. It helps with that. So it's in Iceberg, it's called partition evolution. So if I need to do an evolution of my partition and how it saves on disk, so I'll have fast access to it. If you think about partition, you can think about files that are saved on multiple disks. and I can't read all of them, so I have to understand which one to go through and which one to read first. So if once I know which one to go to and read them, essentially saving lots of time because I don't need to read all my storage. I don't need to do a full scanning. So that's really good that it enables us that partition evolution. Has time travel because of the versions. And because of the versions, it enables us to roll back. So if we did some mistakes, I did mistake in version 1, I can always go to version 0.5 if I wish to. So this is where I can roll back to a previous version or previous point in time. And it increased performance because of the different manifest files and access to it. And it gives us some consistency to it as well, and we'll discuss it. So let's look at the metadata files. The metadata files are 3 files. The first one that defines the table, this is the one at the top. You can see here, I have some draw that I can show you. This is the one. I hope you can all see it. This is my first metadata file that holds all the information about the table. Within that, it holds a pointer. It has the address to the manifest file itself. And the manifest files itself hold a list of other manifest files. So you can see it has different arrows that goes from it to different manifest files. And you can see how this is not exactly a tree. It's more like a graph look-alike. It holds, this is what defines the snapshot. So if my top one defines the table, then I have multiple pointers to the files that define the specific version and the specific snapshot. And the bottom one is the list of the actual data files. So if I have a lot of files saved on disk, I need to know which disk and where to find it. So I need their addresses. So the manifest file, the one at the bottom here, the last one, oops. Yeah, well, looks okay. Actually holds the list of the data files themselves. And the interesting thing here is you can see all these pointers that has these addresses. And this is where the repartition, and also here, the repartition evolution takes place. Because if I have, and I'll just clear it, if I have my manifest files that defines the snapshot, define a specific table version, but now I want to change some of the partition, I don't have to actually change how the files looks on disk. I can only change the pointers and the addresses to reflect how I wish people to query them. So this is the complexities. This is where Iceberg shines. This is also what makes it a little bit less performant in the world of stream processing. And I'm guessing because it's an open source and because the project constantly evolves, we'll see a lot of things improve on that area. So stay tuned. Definitely interesting project and one of the modern table formats that a lot of people are looking into and working with. And I think also today I've seen there was a Snowflake event and they shared that they have they work on supporting Iceberg. So essentially they have Iceberg tables inside Snowflake. So that's really interesting because it enables all the good things that we have here. Any questions so far about Iceberg? Usually this is a place where we got a lot of questions. I got a lot of likes. Thank you, everyone. It feels good. Second one is Apache Hoodie. And Apache Hoodie came out of Uber. And it also works in the shape of layers. Having said that, Apache Hoodie was built, at its core, it was built for streaming. So it was built to support data that changes over time, so it needs to enable fast query on data that changes. So Hoodie tables are considered very, very flexible and explicit. And it lives in a performance trade-off as they offer when they need to handle upserts. So the trade-off here is very different from the two. There's multiple ways that Hoodie enables us and supports its own optimization at its core, and you can actually choose the optimization that you need according to how you work with the tables and how you work with the data. And at its core, there are two new concepts that I want you to learn today. One is copy on write. copy on write means that I have my data on storage. I'm reading it from my compute, but when it's in my compute, it essentially lives in my RAM memory. So I can do all these computations, I can do whatever I want, and I'm going to create a real copy of the data itself only when I actually need to do write. So essentially, I'm giving the user the opportunity to see like it works on isolated data completely, and only when the user actually doing actions such as writing back to storage, this is when I'm going to copy the information. So it's very cheap in terms of versioning, because the versions are not fully copied. They're only being copied on write. And here we have, so specifically with Hoodie, updates are being exclusively in columnar per Git file, although Hoodie has a lot of different updates for different format files, which makes it really, really strong tool. But because updates and copy and write happens only in per Git, it increased the cost of write, but reduced the cost of read, because we already said per Git is wonderful. It enables us to read column by column. Having said that, if I have read-heavy workloads, then I want to do the copy and write operations, and so copy and write with Hoodie or Iceberg works really, really well. The second one you're probably asking is, now I have two different versions of the file. How do I go about that? And in order to go about that, we need to merge them. We need somehow to find a mechanism to merge these files, because we know file is not a table. We need multiple files in order to create a table. So what happens if I write one of my Parquet file, but it actually needs to be part of the whole table? So I need to create some operation that is very similar to merge. So this is where Hoodie enables us to do merge on read specifically. So imagine that updates are written immediately in a row-based files, and now we're not talking columnar per cat, we're talking row-based. We can look at Avro, CSV, etc. And only periodically it's being merged into a columnar per cat. And why do we want to do that? We want to do that in cases where we work with streaming. When we work with streaming, we get a lot of information getting into the system. Usually it's an Avro or JSON format. We process it, we continue on. And the reason for us to want to merge that into a columnar Parquet is when we want to do a more heavy analytics workload that often happens in batch processing or something along this line to enrich real-time data. So Hoodie enables us all these opportunities, and actually more than that. And it's all parts of the log file data that it contains. And the log file data, the layers of metadata, like we mentioned before, we have 3 different layers of metadata that enables us all this operation and optimization, depending on what we config, and some concepts for you to get familiar with. And I'll choose the yellow color. This is the timeline. Because Hoodie at the beginning was built for real time to serve Uber users. So you can see here a lot of the commits are saved in a format of a timeline. So when I have absurd data that arrive between a specific timestamp, and you can see here 5 minutes window time, it's being saved inside a commit. And here I have data that's already split into hours. So this kind of like my real-time commit. This is my more batch processing, and this is where we are incrementally consuming new data overall. So it's split into the timeline, a group transaction that happens on the data, timestamp files. You can see here every file gets its own timestamp, and it's being logged so we can track the changes. And then there's a metadata table where it's the file pruning, if I need to merge, what happens, where it's being duplicated, etc. So we can save only what is needed. So here's a better way to look at that, where we have the manifest file that we know. We see something similar to that with Iceberg. And here it's already the 2 layers that we have, the actual manifest file. What is the table? What are the versions? How do they look on disk? And here Hoodie introduced something called key indexing. The key indexing is already built in, so it enables us to track which files are contained, become stale records. So which file we want to prune, which one we want to delete. And this is another mechanism for compactions. So if we talk about compaction in the format of when we spoke about Parquet, so here we also have this compactions in this world. So if I have stale records, I can easily go ahead and delete them. All right, I'm going to send a push request. Give me a thumbs up. Just let me know you're with me, you understand, and we're good to continue to the next subject. All right. All right, getting some thumbs up. That's good. Cool, thank you. Awesome. Okay. Gotcha. We're on. We're good to go. We got only green thumbs up, which means you all understand and you're all brilliant and we can continue. All right. My last implementation is another open source. It's also very, very loved. And I know there's a lot of folks here that love Databricks and works with Databricks. And this comes from Databricks. They decided to open source it. I think it was 2 years ago or 3 years. I don't remember exactly. And it's another very big tool for modern data format. Yeah, you're welcome. Thank you so much. It's fun. All right, so Delta Lake is its core. It's not part of the Apache. Having said that, it's still open source. It's part of the Linux Foundation. So the Linux Foundation also gives, helps people and companies to open source a lot of the tools that they do. So Data Lake specifically is part of the Linux Foundation. And the way it works is actually much more simple. It's simpler than Hoodie and Iceberg altogether, at least in my opinion. And the way it works, there is a transaction log. So the transaction log, every time we do some changes, we write to the file, we delete, we update, anything that we do, to the table. This information is going to be saved in a transaction log, and you can see here, if I have, this is how it looks like on storage. If I have my table, I'll have another directory for Delta logs. And Delta logs will start holding JSON files that has the commits and the changes that happen to my table. So it holds it in an ordered way. So you can see my JSON goes from 0 to 1 to 2 to 3 to 4. It's ordered. I know what happened when. I know, or I don't care about what happened in a specific timestamp, although I have it there, but at least I know what happened for what. So it gives me the consistency of the operations. And every 10 files, what Delta Lake will do, it will merge them. So I have my checkpoint. You can see it, 10th file of my JSON. It's actually a checkpoint, and a checkpoint for Parquet format because it holds much more information. And my table specifically, usually best practices is to split it according to date, so it's easy for me to reach the file that I need. So if I'm looking for historical files, historical data, specific hour from 5 years ago, it's very easy for me to reach that. So Delta Lake does it in a very, solves this big problem in a very simple manner, relatively, together with the transaction log and the checkpoint file. So you're probably asking yourself, what do we do if you want to look at something, but we don't want to read all the JSON files? So JSON files are being deleted after they're being aggregated, or we can delete it using an operation called vacuum. So actually, we won't have all these JSON small files that can be buggy and annoying. Instead, we'll have only the checkpoint files after we reach them, so it makes it much easier and much more efficient. It also allows Spark, that works really well with Delta Lake, to avoid reprocessing thousands of tiny JSON files, because we don't want to reach the small files from them. So that makes sure that if we want to compute some table state, previous, now, or anything that we do, it's very easy. You Spark only read the Parquet checkpoints files. So it makes it a lot more efficient. There's also more performance optimization that were recently open sourced, that things like key indexing using Bloom filter, Anyone here familiar with Bloom filter? Comment in the chat. If not, it's a good place to ask. It's a good time to ask. Ian, we have a question. Is the 10 checkpoint file name that merge all 0 to 10 JSON files in that checkpoint? Yes. Correct. This is right. You got it right. Awesome. And also we have Bloom filter. We also have Z ordering, which is really, really interesting algorithms in order to do compressions and different optimizations for my data. And it helps me better prune the different files at read time. Very, very critical for me because I don't want to read everything. Like I mentioned, it has a lot of I/O. There's also a combination between Spark and Delta Lake that enables me some caching of the data. Because Spark has caching mechanism. I don't know if everyone here knows. I know there's a lot of Spark users. So Spark has caching mechanisms, so you won't have to read from disk sometimes. But I'm able to cache it and then run another Spark. Another run of Spark is going to leverage what we already cached. So Delta Lakes works with that really beautifully. And behind the scene, it does it for us. So we won't need to think about it. And a lot of more optimization on top of it. And I think we have some questions. Let's take a look. Widely used. Let's see. There's a question, what is Bloom? Okay. Bloom is Bloom filter. And it helps us to know if an object is part of a set. So you can think about if I have a list of different objects and I want to know, or I have a set of different objects, but I want to have only the unique there, then I want to know if a specific object that I'm now looking at is part of this set or not. And it's really critical when I work with big data because I can't go over all the items in my set in order to identify it. And this is where Bloom filter shines. So that's a good question. Thank you. All right. So now we know we have a lot of tables, we have a lot of work, and the question is really, is it enough, right? Is it enough? Now that I have all my different tables, table 1, table 2, table 3, all this good stuff, is how do I know which one to choose, right? It's a big question for us, which one I want to work with. So here's some very high level key measurement to think about. So you want to go with Iceberg if your primary pain point is not changing existing records. But you want to have the right metadata to managing huge tables. So think about it, Iceberg was built for huge tables. Of course, this thing evolves and it changes. But if you have more than 10K partitions, you want to think about Iceberg because it's really optimized for this size. It has really good performance for that, and it works really nice with S3 or Hive MetaStore if you work with that. On the contrary, if you have a lot of deletions, a lot of mutations that you do, and other operations overhead that means data retention and changes, then Iceberg is probably not the best solution for you. Another big question is around Hoodie. I mentioned we had the Hoodie query engine has a lot of different features, and we can tweak it to do merge on read, copy on write. A lot of very good algorithms are implemented in it. So how should I go about that? If you're using different AWS managed services like Athena, Glue, EMR, so you have Hoodie already implemented and pre-installed in them. So it will be very easy for you to take advantage of them right away. Having said that, there is an operational overhead to install and tune Hoodie for real large-scale production workload. Hoodie was tested in Uber for very specific scenarios. A lot of people talk about CDC specifically, and it's not 100% sure if it was tested for real scalable scenarios that often we work with when we do batch processing. So something to think about. What about Delta Lake? If a lot of the operations comes from the world of Spark, Spark and Flink, they have very similar way that they're implemented. The one is for streaming, one is solely for streaming, and another one it's a more of a general shop. So if you are a Spark shop or Flink shop, then Delta Lake is going to work very, very well for you. It was designed to work with them good. It was tested internally in Databricks for some years, and it really brings significant improvements to read and write performance and concordancy. So it definitely can make sense to double down on their this specific ecosystem. If you run your Spark workloads and you manage your analytics and machine learning inside Databricks, 100% go with Delta Lake. It will work superb, and you also get customer success helping you if you need anything specific. Yeah, so it's very interesting if you think about how to go about these three different options. And then my main question for you is this enough? And I see which one should be good for reducing the request cost. Delta, I have seen a lot of cost for requests. Do you mean, when you say request, do you mean request to ObjectStore to list what exists in the ObjectStore specifically? Maybe if you can add a little more information, I can try and help on that front. But my question to you here is, this is great. Let's continue that. And also, are these enough? Are these going to be the ones going to solve my biggest problems? And because I'm asking that, you probably already know what the question is. Probably not. So let's think about the user that we're serving when we're building the data lake. And we can be, all types of folks. We can do data engineering, infrastructure, DevOps, security, analytics, software engineers, all this good stuff. And the question is, do we solve the problems that we're here to solve? And in order to understand that, we need to understand who are our internal customer or external customers. And our internal and external customers are our machine learning practitioners, our BI. We have some cool data analytics folks here today, and our analytics. If we're building dashboard, if we're selling dashboard, if we're building automated smart systems that makes decisions for us, hooray, ChatGPT. Then essentially we're serving all these beautiful folks in our company. So we need to think about different workloads going to serve these folks. So let's take a production case where actually I'm building some analytics for a business. I want to know how their marketing is operating, and I'm building a tool, I'm building the next HubSpot, or anything like that is going to help my customer understand their company business health, essentially. So I might have multiple streams of data coming into my system, real live streams that's coming in, and I can have my batch data. So you can imagine I have my sales stream, I have my marketing stream, I have my leads daily. So one comes in real time, two of them, the two first one comes in real time, second one comes in batch, and I have something that I call main. And main is a combination of all these multiple tables. So I do, when I look at now sales stream, and I'll put it here, I'll this blue. This is my table here. And then I'm doing merge with leads daily. So I want to see what happens in sales, and I want to combine it with leads, and I want to produce some result. But the result here is actually a combination of sales stream, leads daily, and marketing stream. Can you see it? This is going to be number 3. And once I'm happy with number 3, I'm saying, okay, let's expose it downstream to my users, right? So my users are actually going to be here. Hopefully, I'm very bad at writing, but they'll have happy faces. Is that happy? I hope that's happy. Anyway, you know what I mean. So this is a very common workload that we work with when we think about analytics, machine learning, and building businesses. And often the solution that we spoke up till now doesn't really, it helps us, but in very segmented areas. So it doesn't fully give us the whole solution for all of that. And actually, we need to build these. We need to build all the dashboards, automation, data quality, accuracy, rollback for them, troubleshooting, everything that we need for that. So that keeps me at an open discussion for us. When you think about Git, folks, the things that you do in the day-to-day in your organization, what are the challenges that you face with data-intensive application? What are the challenges that you face today with data-intense applications? And there's no right or wrong. All questions or all ideas are good. So feel free to comment here in the chat your thoughts, and I will share mine. So one of the things I usually see with a lot of these teams is collaboration is very to collaborate, especially from the world of machine learning, where we're collaborating on similar data sets. This is one. We want to be able to collaborate on them in parallel. Second one is coordinating the efforts of multiple machines or team members. It's also come from the world of collaboration, but we're taking it to the next level, saying, I have multiple machines going to access this data. I want it to be in a good shape. I want to make sure that every time a machine accesses this multiple tables together, it comes in a good shape. I have always the challenge of distributed applications that do writing and reading at the same time. So if we're going back to our workloads for a second, I had here all my application that's doing all the write, merge. But what happens if at this point of time, so we can think about here as a timeline, I have timeline with number 1, I have timeline with number 2, right? So my data, my cell stream, once I'm reaching here, number 2, already changed. So this is number 2 here. And because I merge it with my daily, I can only see something that kind of like slightly of the past because of the journey it takes me to merge it here, bring it here, and do all the operations on it. It can be a matter of milliseconds. Sometimes it can take a little bit longer. You can imagine that this is a Spark job that it's running that takes sometimes longer than we expected. And consistency and atomicity is often missing. If we spoke about the different table formats, it gives me consistency and atomicity in all the operations I'm doing here and in all the operations I'm doing here. It doesn't give me consistency and atomicity of all this process together. So I have 4 tables, right? And this is essentially 3 tables, and this is my end result. But I want to be able to have atomicity on all the operations here. So if something here failed, the whole process would essentially fail. Does that make sense? Give me a thumbs up if that resonates and you understand what I mean. It's really critical for us to get it right here. And feel comfortable to ask questions if something doesn't feel right. Yes, and also the great challenges of data governance and data quality. 100%. %, here. Well done. All right. So I'm getting some thumbs up. Thank you for the love. Yeah. So, and this is the main question for us to solve today. What can we borrow from engineering, software engineering best practices, processes, and bring them to the data world? So I see one with a thumbs down. If you want to share, maybe I can go over again some of the information and where everyone to stay with us and understand. If you can share in the chat, I'll make sure to address it as well. All right. So a quick overview of what we know from engineering continuous principles. One is repeatable, reliable process. If I release a software to my production, I can revert back. I can roll back a previous version. It's all good. This is a process that is repeatable. and I can rely on it. Second thing is automate everything. Usually when I think about building software, I want to be able to automate all the process. So I have GitHub Action for testing and all this beautiful stuff. I'm relying very heavily on the development lifecycle because my repeatable processes are something that are strictly built into building blocks. And I usually have something like manual checklist or a playbook or a list of tasks that I want to perform manually or automatically. This is what I call repeatable processes, just to give you a little bit more information. And automation is a very, very important part because once I have these playbooks, I want to automate it because our time is very expensive and we should be very conservative how we spend our time on different creative exercises instead of tedious playbooks task running. So if we have a specific manual process and it's not really repeatable or reliable, until it has been committed to code and is executable automatically on demand, we want to be able to automate it. In order to automate it, we need to have version control because we want to protect ourselves from a wrong execution. So we want to have multiple versions. We want to be able to manage these versions so we can able to go back. And version control is also one of the cornerstones of continuous deployment. So continuous integration, I'm integrating the code, and continuous deployment, I'm running some testing, I'm happy with the result, I can always deploy my software to production, and I can trust the process because I have version control. So version control here is absolutely must for every software project. Smart folks here said data quality. So I want to build in quality. It comes from data engineer. We have a lot of teams that are responsible for quality. We have a lot of engineers that are responsible for quality. And usually quality is baked into every step that we do with software, starting from development all the way to staging. And later on, when I have software that runs in my production, I have a system that monitors that everything is okay. Another thing is from continuous principles is do the hardest part first. Often painful, time-consuming, error-prone tasks compounds over time. So we want to be able to do the hard first. We run with ownership model most of the times. I don't know if people here have felt it. Everyone is responsible at the end of the day, and done mean released. My software is released, is available for to create value for my customers. And we have a system to continuously improve. So the CD itself doesn't really stop at deployment. The feedback loop is actually in the heart of the CD. If anything goes wrong, if anything happens inside production, or any monitoring or observability, sometimes I have observability systems, that this is where we have the continuous improvement. It's really in the heart of software engineering. So how do we, and an industry, adopted CI/CD? I know there's a lot of good DevOps folks here, so maybe you already implemented or you start to implement CI/CD for your software lifecycle. So maybe you want to share and jump in and say, how did you adopt CI/CD for your teams, for your company? How did you go about that? So this is actually our time to think through how do we adopt CI/CD, and a lot of the times we did it in small phases. It can't really be overnight. It can't really be something that we do right away. It's something that we always do in incremental phases. We start very small. We start with experimenting. We see that it works, and we slowly integrate it into more and more parts in our system. If I